Hello, my name is Stuart Kaler, and I'm a teacher here at Archbishop Rudin High School in San Francisco. I teach the subjects of physics, computer science, and engineering. And I would like to briefly give you an introduction to our summer Army reset lesson plan called Hit the Target, an exploration into projectile motion. Just to give you some motivation and background as to this lesson plan, I want to tell you that I was very inspired by my work this summer at the Yuma Proving Ground in Yuma, Arizona, or YPG for short. The YPG is the Army's testing ground for all manners of equipment and armament before they're given to troops in the field in order to cut down on casualties. Their motto is truth in testing, and I saw them live that motto each and every day. True professionals. One aspect of my summer research was the recording of projectiles in flight to see that they met Army specification. And we had all manners of sensors and telemetry to record these aspects of projectile motion. And this was the primary motivation for this lesson plan. So without any further ado, I give you Hit the Target.
Hi, my name is Nancy Rubin, and I am here to talk about the engagement portion of our project. Students are going to start by watching some videos of projectiles to spark their curiosity. The teacher is going to guide the discussion with some prompting questions so students think about what affects how far and high a projectile travels. We've chosen to introduce the lesson with some engaging videos. So we will introduce projectile motion with some YouTube videos so that we can engage students with the questions. What path do you think the object follows? And what variables might determine how far or how high it goes?
To give you some brief overview of our exploration section of our 5E lesson plan, I just wanted to give an introduction to the projectile simulator that comes from this physics classroom. As you can see, it's a pretty robust simulation, and there's many things that you can record and gather data with. You can see these active buttons can either trace the path of the projectile, show the velocity vectors, both vertical and horizontal, and the acceleration vector, which is always going downward per g, 10 meters per second squared. You can also set with these slide switches different speeds. So we'll just set it at 40 meters per second, and an angle, initial angle for the projectile, and we'll set it at 45. And so I'll launch this, and you can see that it starts recording the path, and you can see the varying velocity vectors altering during the course of flight. You can also see up here, which is recording of the time as it goes, and you can either move backwards or forwards as you like, as the students like to record data. So for example, if a student wanted to get the apogee of this, it looks like at 40 meters per second, 45 degrees of initial angle, the apogee is about 40.78 meters at 28 seconds. And then you continue on with this simulation until it hits the end. But once it hits the end, and once these arrows go away, you can no longer toggle them back and forth. You would have to reset and restart the simulation. So the various aspects of exploration is the students can now graph these various projectile paths with these initial variable settings. I would now like to give a brief overview as to the explanation part of our 5E lesson plan for Hit the Target, an exploration into projectile motion. And I will refer you to the teacher content document, which is linked to in this section of our 5E lesson plan. Here you will find a discussion for the teacher to guide the students' exploration and explanation as to what they see by detailing the physics of projectile motion. And it goes through Newton's laws of motion, both first law of motion and second law of motion, and I think the language here is fairly self-explanatory.
Welcome, educators. My name is Delmar Wilson. In this portion of the 5E lesson, we'll walk through the elaborate and evaluate phases, where students move from guided exploration to real-world application and demonstration of their learning. In the elaborate phase, students take on the role of a test officer. Inspired by real-world careers like that of Ashley DeShetto, their mission, design and optimize a project launcher that hits a designated target precisely 60 meters away. Using the PhET projectile motion simulation, students work collaboratively to test and refine angle and velocity settings. They record data from each trial, analyze the effects of gravity, and justify their choices using core physics vocabulary, such as range, velocity, acceleration, and optimal range. Teachers actively guide the process, posing strategic questions like, how does velocity impact your trajectory? Or would your results change in a different gravity environment? These interactions serve as formative assessments to assess student understanding and reasoning. Through experimentations, students reflect on their process, revive their predictions, and prepare a brief summary of their final strategy. In the evaluation phase, students synthesize their findings into a 5-slide presentation, communicating their design process, data analysis, and conclusions. This performance task reinforces this understanding while building real-world communication skills. A sample outline can be given to students to guide students' organization and presentation of their findings. A clear and structured rubric is accompanied to evaluate understanding of physics concepts, the use of data, strength of justification, and team communication. This ensures every student is held to high expectations with multiple ways to show mastery. Through this engaging, standards-aligned learning sequence, students don't just observe project motion. They experience it, test it, and communicate it like real engineers and physicists. We encourage you to adapt this lesson to meet your learners' needs and bring science to life in your own classroom.